Hey everybody, it's Rachel, your very favorite Chem 101 SI. Here I am sitting in this empty classroom before I teach an SI class. I have had quite a few questions and some confusion about intermolecular forces and polar, non-polar. So I wanted to kind of make a little video to talk about that. So I'm going to switch around and see if I can turn on my screen record, and hopefully we can work it out together, okay? Okay, so here we go. Hopefully this will work. Okay, so when we're talking about polar or nonpolar, essentially what we're talking about is how the electrons are distributed around the entire molecule. Okay, so if I have an atom, and here's my nucleus, right? And it's nonpolar, we would expect that there would be electrons pretty much evenly dispersed all the way around the electron. Whereas if I have a polar molecule, I'm going to expect to see more atoms, or more electrons, in one area of the molecule, and maybe not quite as many in the other spots. Okay, and so if I have a ton of electrons on this side over here where I tend to see them, and I don't have as many electrons on this side's going to be slightly positive, and this side's going to be slightly negative. And just kind of like the way a magnet is, one side sticks to your refrigerator and one side doesn't. One side, they have different poles, right, on a magnet. So just kind of like that, we've got a positive side and a little bit of a negative side, and so that's polar. So if I have a molecule that is like CH4, so here's an H and an H, H, H. Okay, CH4 is a non-polar molecule because it's only C's and H's. And remember, we talked about how C's and H's are always non-polar. A CH bond is always non-polar, right? Okay, so this is a nonpolar molecule. We know that right now. And that means that I would expect to see my electrons generally scattered pretty evenly throughout my entire, like around my entire molecule. Whereas with a molecule like water, here's my oxygen, here's my hydrogen, here's my hydrogen. Now I know with water, it's got 6 valence electrons, and I've only used one here and one here. So that means it's got 2 lone pairs, one here and one here. Now, oxygen is relatively electronegative, especially as compared to hydrogen, so it's going to kind of want to hog these shared electrons, which means that these hydrogens, because they're sharing their electrons with oxygen, they tend to be a little more positive, because we tend to see the electrons a little bit more on this side over here. Okay, and this hydrogen here is also a little bit more positive. Now we also have these lone pairs on this side right here and right here, and those electrons are for sure negative, right? And so because oxygen tends to hog the electrons, and because it has these lone pairs here, this side of the molecule is, this side of the molecule is going to tend to be pretty negative. In other words, if we're looking for electrons, we're more likely to find electrons on this side of the molecule, right, than we are on this side of the molecule. So we're going to have something a little bit more like this when it comes to water. Now, because this part of the molecule tends to be a little bit more positive, and look, that looks like a little happy face there, and this side of the molecule tends to be a little bit more negative, it's going to, just kind of like a magnet, want to sort of sneak a little bit closer to something on the side that might be a little bit more positive, and something on this side that might be a little bit more negative. It's going to tend to want to do that, just like the way that a magnet is going to tend to want to stick to something of the opposite poles, right? Now this bond isn't super duper strong. It's not as strong for sure as these bonds right here, those covalent bonds, but it is a relatively strong thing, and this type of bond is only going to be available when we have a polar molecule. So it's important to understand which thing is polar and which thing is not polar. And remember, we talked about our rules of polarity. So if I have 3 molecules and they're all the same, and I have a lone pair on my central atom, this is going to be polar. If I have another set of molecules, and let's say the outside ones are different, but there's still a lone pair here in the middle, that's going to be polar. And if all my molecules are different, then that is also going to be polar for sure. Okay, so these are our polar molecules. If you don't have a chart with your electronegativities nearby, which most of the time, let's face it, we don't, we can generally get a good idea as to whether something is polar or nonpolar by understanding these rules. Now, in addition, we know, for example, that water, when we draw its electron geometry, it's going to be tetrahedral, right? It's going to be O, and then it's going to have 2 electrons here, and 2, let me see if I can get that back. There we go. And 2 electrons here, right? And then we're going to have this hydrogen that sticks out towards us, and we have this hydrogen that kind of goes back into the page, right? And so we see that it is tetrahedral in electron geometry, but we don't use these electrons when we are making molecular geometry, and so we end up with a molecule that is bent because of the influence of those lone pair electrons, right? Okay, so because our electron shape here, geometry is different than this one, we also can see that it's polar because these empty electrons right here have changed the shape of our molecule. Okay, so once we understand whether something is polar or nonpolar, that's going to help us begin to determine what kind of intermolecular forces we have, right? So our intermolecular forces, we call those, whoops, let's change onto my actual drawing. Let's use this one. Our intermolecular forces, we call those IMF, intermolecular forces. We have 3 kinds, right? We have dispersion forces. We have dipole interactions. And we have hydrogen bonding. Okay, so how do we know which of these forces our molecules are going to have? Because we need to be able to figure them out so that we can figure out how the molecules react to each other, how high their boiling point is, their melting point, whether they can dissolve in water. All of those things are determined by their intermolecular forces, okay? So I find it easier to talk through this a little bit if we kind of have a chart to help our thought process. So let me clear this off here, and we will start in that direction, okay? So the first thing when we are looking at molecules, the first thing that we have to do is figure out if that molecule is ionic or covalent. Because if it's ionic, it doesn't really have any intermolecular forces. Those molecules are kind of different. They don't really have that bonding. They form themselves into that crystal lattice, right? And so the way that they work is different. And so ionic, we're just going to say they don't really have any intermolecular forces. So if it's ionic, we're just going to say no, and we're going to stop, okay? If it's covalent, though, so let's say, yes, it's covalent. Okay, if it's covalent, that's great. Well, we know that all covalent molecules have dispersion forces. Okay, so let's say yes, dispersion forces. Okay, but also now we need to think about, is this polar or nonpolar? Okay, so let's say this side is polar, this side is nonpolar. Okay, well, if it's nonpolar, it can't have any dipole-dipole interactions because those dipole-dipole interactions require some kind of polarity, right? Those dipole-dipole interactions are what we were talking about before when we kind of had those like refrigerator magnets that were a little bit positive on one side and a little bit negative on the other, and they draw each other together. Those are dipole-dipole interactions, and we can't have that if we don't have a dipole to start with. And so those things have to be polar. So if our thing is nonpolar, then we have to stop because we can't go any further. We don't have a dipole. So if it's nonpolar, we're just going to say no, there's no more forces. We're just going to stop. Okay? No more, let's say that. Because they do have dispersion forces here, because all covalent bonds, molecules have those dispersion forces, right? Okay, so every covalent molecule has dispersion forces. Okay, so now let's say that we do have a polar molecule. Okay, if it has a polar molecule, that means that it's got that partially positive side, it's got that partially negative side, so we know that it automatically is going to have dipole-dipole interactions. Okay, so then the next question that we have to ask each other is, can it hydrogen bond? So let's go this way and say yes. And on this side, we'll say no. Now, in order to say yes, that means that it has to have bonds that are between a hydrogen and a fluorine, a hydrogen and an oxygen, and a hydrogen and a nitrogen. If it has any one of these bonds, then we're going to say yes, it can hydrogen bond. If it does not have any of those bonds, then it's no, and we're just going to stop. Okay? So if it does not have a bond between a fluorine, an oxygen, or a nitrogen with a hydrogen, if it does not have those, what it does have is dipole-dipole and dispersion forces. Okay? If we're stopping here. If it does have an HF, an HO, or an HN, then it can hydrogen bond. So we're going to write that there. Hydrogen bond with itself. Okay? So if I just have this hydrofluoric acid, this HF here, right? I can hydrogen bond another hydrofluoric acid to these atoms in the molecule, because I can do it to the H and I can do it to the F. So we draw that hydrogen bond with just like a dotted line, and the fluorine here is the negative part, right? And the hydrogen is going to be the positive part. So the hydrogen is going to go with the fluorine, HF, and this hydrogen here can also bond. It's going to go with the fluorine. So what we're doing is we are sandwiching this hydrogen in between these fluorines, right? This hydrogen is sandwiched between these fluorines. This hydrogen could be sandwiched between these fluorines, right there, like that, right? And so because it can hydrogen bond to itself, that means that it has sort of a greater attraction. Because it can want to stick together with those molecules, it's going to have like a higher boiling point. It's going to be harder for these molecules to split off and float around everywhere like a gas, right? It's going to take more energy to get them to do that. And so because they can hydrogen bond to each other, that's going to make a big difference in its boiling point. And we could do the same thing with, like let's say I have like a methanol, OH. This is an H, and this is an H, and this is an H. Okay? This is an alcoholic compound. Now it's got an OH here. right? It's got this OH bond. So because it has this OH bond, it can hydrogen bond to itself. I can hydrogen bond this right here to an HO with a C. And this H right here, I could do it with the HOC. Okay, like that. And so again, this compound is going to tend to be have a little bit of a higher boiling point than an atom that like didn't have this OH here and it was just like a CH4. Okay, so that pretty much I think takes care of hydrogen bonding. Let me think if there's anything else I want to tell you. Oh yes, so when we are talking about hydrogen bonding, there's two ways that we can hydrogen bond, right? We can hydrogen bond with itself, right? And that's what we're talking about here. But also, it would be possible for something to hydrogen bond with water, because water can hydrogen bond with other things, right? So, like for example, I could take this methanol, and I could take this oxygen, and I could bond it with water. Right? I could take this hydrogen and I could bond it with water, right? And even if I had something that maybe would not necessarily bond with water otherwise, like let's say we had a C with a CO and an OH here, right? This is a carboxylic acid. And so normally we would say that this part of the OH, or this part of the acid, would be able to hydrogen bond with itself, right? But this part of it would not be able to hydrogen bond with itself because it doesn't have an H attached to it. It has to have that H attached to it in order to hydrogen bond with itself. So we're going to get rid of that. Get rid of that. Okay, so I could hydrogen bond here with this HO, and then we have a C and a C and a O right there, like that. I could do that, sure. But I could also hydrogen bond with water like that. Okay, so when I have an O, or when I have an F, or I have an N, I could hydrogen bond those things with water, but they might not hydrogen bond with themselves. So that's just something to think about, like when we talk later about solubility, don't freak out about this right now. Okay, that's just something I wanted to bring to your attention for later. All right, well, I think that's everything I want to talk about. So let me know if you have any questions. As always, I have SI and office hours available. So make sure you find me if you have trouble. Talk to the tutors in the Learning Center or to your professor during office hours. We are all here to help you be successful. So there's no reason for you to be confused. Just reach out for help. Thanks. Bye.